All right. Well, welcome everyone. Thank you so much for coming. It's a beautiful day out there, so thanks for heading inside to hear about ocean drilling. Adriane Lamb, our speaker tonight, is an assistant professor at Binghamton University, where she's recently completed her postdoctoral fellowship. Now she's continuing her work as a paleoceanographer, a paleontologist, and works very heavily in science communication. I got to know her on Twitter way back in the day, and she was always tweeting interesting stuff about forams. So I'm excited she's here live to tell us about ocean drilling. Please welcome Dr. Adriane Lamb.
Thank you, and thank you all for being here tonight. I appreciate it, and I appreciate the invite to be here to talk. So, I can't do this. Can everyone hear me okay? All right, I tend to walk and wander while I talk. Okay, so I'm going to tell you all about the 3 expeditions that I've been involved with over the years. But first I just want to give a quick introduction. So I'm originally from Beaver Dam, Virginia. So I'm from the southern part of the US and very rural. So I grew up swimming in ditches, playing outside, climbing on trees, and that's where I developed my love of nature. Luckily, my parents didn't tell me to get out of the mud or get away from that tree. I then went on to community college after high school, and I do want to note that I hated K-12 education, and I swore to never come back into education again. And here I am as a professor, so I find that kind of odd, but I love it. So after I actually then went to community college, I really wanted to do a career that let me travel and do neat things. I wanted to be outdoors and meet new people. So after high school, I went to community college, and I wasn't sure what I wanted to do. But it was there that I found geology, and then I decided that I wanted to major in it. So I did my Bachelor's of Science at James Madison University, which was in the Appalachian Mountains of Virginia. And then I decided to do my Master's of Science at Ohio University, which is in kind of southeastern Ohio. And I thought I wanted to work in oil and gas, and then I realized, no, I don't want to do that. And I had met this advisor at UMass Amherst that I really liked and was working with on forums when I was an undergrad, Mark. So I was at this oil conference during my master's degree, and I thought, this is ridiculous. I don't want to do oil. I want to be a biostratigrapher, and I'll explain what that is later. And I wanted to be a paleoceanographer. So I emailed Mark and I said, can I come do a PhD with you? And he said, now's the perfect time. I'm having a huge lab turnover. So long story short, I ended up getting my PhD from UMass Amherst in Western Massachusetts. And then I did a postdoctoral fellowship at Binghamton University, just in the southern tier, about 4 hours from here. And they liked me well enough. I love them. So they kept me. So I'm an assistant professor there. I just started in January. So I'm also a first-generation academic. I'm the first in my immediate family and from those family members that I interacted with most to get a bachelor's, master's, and PhD. So for a long time, I didn't feel like I fit into academia because I grew up very rural, and I was first generation. So this is me playing with the T-Rex. This is Triceratops. This is a holotype of Triceratops. It was the first skull found and named for that genus and species. This is in the back of the Smithsonian. I did touch it because how can you not? And this is my lab group from last year, and this is my lab group this year. We just went to the Franklin and Sterling mines over in New Jersey. So here's just a roadmap of where we're going with this talk. Part 1 is just going to be a quick introduction of scientific ocean drilling and the history of scientific ocean drilling. What is it? Part 2 will be about Expedition 371 that took place in the Tasman Sea. Part 3 will be Expeditions 390 and 393. These were expeditions that sailed separately, but they were implemented as a joint program. So kind of they behave as one expedition together. Part 4 is Expedition 403. It's the last expedition that will sail, the last expedition of the Joydes Resolution, this drill ship. That'll take place in the Arctic Ocean, so I'll end on that. And then I'll wrap up with some conclusions and take any questions you have, and I have some fun show and tell stuff up here as well. Okay, so let's get into it. So quick intro and history of scientific ocean drilling. So scientific ocean drilling is basically when a team of scientists, staff, and crew all go out into the ocean on a ship. This is the Glomar Challenger. It was one of our earliest drill ships to recover sediment cores from around the global oceans. And we use technology to core these sediments and rock from the seafloor and use those sediments and rocks to reconstruct Earth's history, whether it be climate, tectonics, so on and so forth. The purpose of scientific ocean drilling, or SciOD for short, is two-pronged, mainly. Science and society. In the science realm, what we do is investigate the ocean and the atmospheric response to past climate change events and relate those to modern climate change due to humans. We also deciphered tectonic activity and how tectonics and plate tectonics work. This is a big scale process, and there's still a lot about this that we don't know. And on the biotic end of things, we also went in for how evolution and extinction processes, especially for marine organisms, like zooplankton, for example, how those processes behave in the open ocean and what causes speciation and extinction. And again, how are these organisms going to respond to a warming climate by looking at how they responded to those climates of the past. On the society part of things, one of our jobs is to train the next generation of scientists. So that's what I do with my PhD students, by them doing undergraduate research, theses, and dissertations. We also want to educate the general public about what we're doing in our findings. IODP and scientific ocean drilling is funded by the National Science Foundation. They're giving funds from Congress, and Congress gets money from you all and me, taxpayers, so thank you. So because that science is publicly funded, we want that to be open access so that you all know what cool things we're up to and what we've learned. And that's kind of what we're doing tonight, educating the general public, whether that be students, other professors, people that just love science about what we're doing. And also, very importantly, we want to communicate our findings to policymakers. So we are involved in policy. Some of us are not. I don't do that. But some of us are very involved with that, and we do have programs. Okay, so let's get into a quick history of scientific ocean drilling. And this really started with this cool project called Project Mohole that started in the 1950s. So basically, a bunch of dudes got together and said, hey, wouldn't it be cool if we drilled a hole in the ocean and we drilled through the Earth's crust into kind of the lithosphere. It's called the Moho discontinuity. Wouldn't that be neat? And other people said, yeah, that'd be really cool. And then they gave them money to do it. I'm paraphrasing, that's a short story. If you want to hear the whole story about how that happened, there's this really wonderful book written by Willard Bascom, A Hole in the Bottom of the Sea. And it's about this entire story of Project Mohole. So they took this oil drill ship called the Cuss 1. And you can see that it's got this drill rig in the middle of the ship. They went out to where they thought the Earth's crust was very shallow, and they started to drill. Drilling didn't go as planned. They didn't actually make it into the Moho discontinuity, but they did make it 601 meters into the ocean sediments. So what they recovered were sediments down to the Miocene. So the Miocene age sediments were from 23 to 5 million years ago. And what they realized were that these sediments actually contained a really phenomenal record of Earth's climate. So either through the sediments themselves or the tiny fossils and microplankton that were contained in those sediments. So this started to get the attention of a lot of US folks, and they decided to develop a scientific ocean drilling project that included more scientists and was government funded. So this is where the deep sea drilling project was born. So this started in 1968, and until 75, it was only US funded. But then this got the attention of our international partners. So then Germany, Japan, the United Kingdom, Soviet Union, and France all started paying into the program and helping fund expeditions so that their scientists could too sail on, then was the Glomar Challenger, the second drill ship that we got, to go drill and sail in the seas. So what really was cool that came from DSDP was the cores that they drilled on leg 3, the third expedition to sail under DSDP. They recovered cores that provided evidence for the theory of seafloor spreading and plate tectonics. So very cool. After that was the ocean drilling program. This was from 1985 to 2003. This also included 17 partnering countries. The US, of course, provided the most funding. And we got a new drill ship then, the Joides Resolution. So this is a ship I'll talk about a lot during this talk. It was actually built in Canada for an oil ship, but when this ship was built, I can't remember exactly when that was, the whole industry was dipping. So we bought it, retrofitted it for drilling sediments, and that's what it does now. Okay, in 2003, that program was renewed and we called it the Integrated Ocean Drilling Program. It was really this program where we implemented new drilling techniques so that we could drill deeper into the sediments, recover more complete sediment sections, but also recover a lot more like rocks under that sediment, so seafloor basalts. So we really learned how to drill better. And that lasted until 2013. A lot of people didn't like the word drilling in there, rightfully so. So we dropped that, and then the next phase of IODP is the International Ocean Discovery Program, and that ends this year, unfortunately, well, next year. Right now, we have over 24 partnering countries, and we use multiple drill platforms, not just the JR. So the European countries, they operate the mission-specific platforms, or MSPs. These are platforms that you basically put into the ocean via another ship. They can drill very shallow, like in coastal regions or on reefs, and they can drill like 1 or 2 holes that are very close to one another. The JR we'll talk about a little bit more, that's US funded. So again, taxpayer dollars. And then the Chikyu is much larger than the JOIDES resolution, and it's a lot more expensive to operate. This ship is funded and operated by Japan, and it's made to drill into the really deep water column and then recover rocks. It does in most of its drilling in the Pacific Ring of Fire to study tectonics and volcanic processes. But the JOIDES is what we'll focus on. It's really cool. So it's a research vessel in addition to being a drill ship. So number 1 is the derrick. This is the entire structure in the middle of the ship that holds the drill string. So we have a heave compensator, which I'll show you in a minute, and that holds the drill string and the drill bit. There's a hole in the middle of the ocean, in the middle of the ship where we pipe the drill string down to the seafloor. There's also a catwalk. This is where we store core. The catwalk was actually moved to the front. But now this part of the ship in the back is where we store all the pipe to drill and make the drill string. And in the front, the very top is where the captain and crew work and live. This middle part is where in the back is where all of our labs are. And then we all live under here. There's just a bunch of small rooms. The JOIDES resolution itself is about 1.5 football fields long. So it's a pretty big ship. And the derrick stands about 5 stories above the water surface. So we're talking about a pretty substantial ship. The JOIDES does riserless drilling. So what that means is that we pipe the drill string to the seafloor, we drop the drill bit down, and we pump seawater into that hole to keep everything lubricated and from not getting too hot. We don't keep the cuttings, the sediment that's created in rock by that drill bit on either side, on the outside of that drill bit. It just goes onto the bottom of the seafloor, and we don't recirculate that seawater that we pump down. This is in contrast to what the oil companies do. They're pumping different fluids down that hole to lubricate everything and keep it cool and running smoothly, but they also keep the cuttings. They're bringing everything back up onto the ship. So riserless drilling is easier, it's cheaper to do, and it's totally environmentally friendly. We're using seawater. These cuttings are just left on the seafloor. They're just sediments. It's all good. These pictures are showcasing the derrick, so that feature that stands about 5 stories above the water level, and that's an image looking into it. And this yellow piece here is called the heave compensator. So this is a really important part of the ship and an important part of drilling. The heave compensator, like its name suggests, it compensates for the heave. So when we're in the middle of the ocean, you still have waves, and the ship is doing this, going up and down, up and down. That heave compensator keeps that drill bit and the drill string steady. So if you look at it, it looks like the heave compensator is going up and down, but in reality, it's the ship that's going up and down around the heave compensator, because we don't want the drill bit bouncing up and down on the bottom of the seafloor. We want to recover good sediment. So here's folks that work on the drill string on the drill floor. What they're doing, this is a pipe. They're screwing on into another section. They're going to drop that down into the hole in the middle of the ship. And they're going to connect another piece of piping. And that's how they build the drill string all the way down to the seafloor. And that's one of our drill bits that we use. So the sediment goes through the center, and that's what we keep. It goes up into that drill string, and then we pull it back onto the ship after we've got 10 meters of core. Okay, so here's another picture of that derrick. Here's that heave compensator right in here, and I'm going to show you the short video. So what they're doing is taking the heave compensator, they've put a piece of drill piping onto it, and they're going to push that down through the hole in the middle of the ocean. They're going to connect it, untwist it from the heave compensator, and then connect another piece of pipe to it. They're going to do that over and over again until they build that drill string and it reaches the bottom of the seafloor, and then they're going to drop the drill bit and start drilling. The other thing that we want to do when we're out at sea is keep the ship very steady. It cannot move. So there's vertical movement, there's horizontal movement. For the horizontal movement, the ship has 12 thrusters. When we're moving, these thrusters are put up. When we're at the drill location, they're put down. And what they do is they very precisely keep the ship within a 10-meter square. So this is the moon pool. That's the drill string. This is that hole in the middle of the ship. So that ship does not move outside the area of that moon pool. So those thrusters keep us in place, again, because we want to recover the best sediments and rocks that we can. Okay, so this is a map of where we've drilled thus far. And you'll notice that it's very global. The colors indicate the different programs that I just talked about and reviewed with you. And there's some places in the global ocean that we haven't drilled as much and we don't know much about, like the South Pacific and the Arctic Ocean. Or I'm sorry, that's not the Arctic Ocean, that's the Southern Ocean. And up here in the Arctic. And there's some places where we've drilled a lot. So for example, around Japan, again, there's a lot of earthquakes. We want to study how those earthquakes happen. Can we predict them? And also subduction zones and such like that, and of course the North Atlantic. But our story is going to start here with IODP Expedition 371. There's 6 pink dots in the middle there, and those are the sites where we drilled in 2017. So let's talk about the Tasman Sea, and this is an actual picture that we took while on the expedition in the Tasman. When cool things happen, like big double rainbows or pods of dolphins or whales, the captain will come on the ship and let us all know. So this was a beautiful double rainbow after a choppy storm. You can see the white caps in the waves. It was very windy. Called us all out, and we got this beautiful, beautiful picture in the Tasman. So our story starts with the identification of Zealandia. This is Earth's newest named continent. And in 2017, Nick Mortimer and his colleagues officially named the continent. So they work at GNS, which is like the USGS for New Zealand. And with the publication of this paper, they said this is a continent. We know this is a continent because all the area around New Zealand and New Caledonia within this red dotted line has continental rocks that characterize continents, not ocean seafloor. So there's some pretty cool things about Zealandia. So what you're looking at is a bathymetric map. So the light blue area is the ocean floor. Where it gets darker, that's deeper. And this dotted red line, again, is the outline of Zealandia. So here's New Zealand and New Caledonia is to the north. And you can see here's the Australian plate that has Australia on it. Notice also there's this big subduction zone that runs through New Zealand. It's why they get massive earthquakes and also some volcanic activity. And here is that subduction zone, kind of a cartoon of it. I'm sorry for the wording here. It kind of melted my brain when I looked at it because I flipped the image. Just so you can see that there's this subduction zone of ocean crust, and here's a continent, just like what that would look like. So we have this big plate that's subducting under the continent of Zealandia. So Zealandia is different from other continents. 94% approximately of that continent is submerged below the seafloor. It consists of about 4.9 million square kilometers, so it is much smaller than some other continents. And again, we know Zealandia is a continent because we've done seafloor dredges where they drop a huge bucket off of a ship and just scrape the bottom of the seafloor. And all of that stuff that we get back indicates that this is a continent, not an ocean seafloor. So there's some outstanding questions with respect to Zealandia and the subduction zone and climate in this region. The first is, how do subduction zones begin? So here's that same subduction zone. We have that cold, old crust subducting or sinking underneath of this continental crust, which is much more buoyant. We don't know how this starts exactly. There's a lot of different models for how that happens. We also don't know much about the ancient climate in the Tasman Sea. What you're looking at on the right side of the screen is a climate model from Hollis and others in 2012. And this is representing sea surface temperature data from about 40 million years ago in the Eocene. What they've done is modeled this data, and they're finding, so there's this big question mark here, there's a mismatch between what their computer models say the temperature was and what other data says the temperature was, or proxy data from fossils and other biologic fossil material. So we need more data about what was the temperature there even like in deep time. So to answer these two outstanding questions, what we did was go and recover sediments from around the Tasman Sea to investigate how the subduction zone formed that cuts through Zealandia and New Zealand. And we also were to recover sediments to reconstruct the ancient climate in that region. So we drilled 6 holes to achieve these objectives. So again, you're looking at this map of Zealandia and those 6 drill sites highlighted. So we drilled 2 on Lord Howe Rise, So again, the warmer colors are indicating more shallow areas. So this is a very shallow water feature. 3 are in the basins surrounding Lord Howe Rise. So those were the ones that we targeted to look at tectonic activity. And we have one that was really quite fun in pink here circled. In the abyssal plain, that was like outside of the continent of Zealandia. And that was a really fun site. I'll talk about it more in a minute. So with the start of Expedition 371, we had a lot of fun, my husband and I. So first of all the scientists were to meet in Townsville, Australia, and that's where we board the ship. So IODP, it pays for the scientists' flights down to the port city, and they will also pay for you to stay in a hotel prior to boarding that ship. So we totally took advantage of this and had a delayed honeymoon. So we went down to Australia about a week early, and there's this little island called Magnetic Island off the coast of Townsville. We hung out there for a week. We snorkeled the Great Barrier Reef, saw some humpback whales breaching. We stayed with wonderful Airbnb hosts that showed us koalas, flying fox bats, which were just gorgeous. And I even found some brachiopods, some modern brachiopods, which I just geeked out over. It was awesome. So we board the ship about 2 days early. And prior to our expedition, my PhD advisor, Mark, who's here, was on the ship with a School of Earth Science teachers. And they do this program called School of Rock. So these professors, and there's Lisa White, she's another professor and curator in the UC system, they get these educators together, they put them on the ship, they sail from one port to another when the ship's in transit, and they teach them about scientific ocean drilling so that they can go back and take that information to their classrooms. So we had this cool crossover party with the participants of the expedition and these teachers and everyone. We had a blast. But for those 2 days before we get on the ship, what we do is basically just get acquainted with what we're doing, our lab spaces, finding our way around the ship. Oddly, it's very kind of maze-like on the ship. And just start testing out the equipment and getting adjusted with life on the ship and start getting on our shifts. So everyone works 12-hour shifts. You're either on the midnight to noon or noon to midnight shift. It sounds awful, but honestly, I loved it. It was really cool. And they cook for us. They do all of our laundry. So you are there solely as a vehicle to do science. Everything else is taken care of. It's awesome. So everyone on the ship has a job. No one is there just to piddle around. So my job was a planktic foraminiferal biostratigrapher. So that's a big word, let's break it down. So bio means life, and stratigraphy is a branch of geosciences that, in part, works with assigning age to the rock and sediment record. So what I do is use fossils to tell the age of sediments. These are planktic foraminifera. They're the marine plankton that I work with in my research and in my lab. And I use when they went extinct and when they evolved to date the sediments into which we're drilling. I kind of like to think of ourselves as time lords of the sea. I don't know if there's any Doctor Who fans in here. I've never watched it, but I know a lot of people do. Because we have control over telling folks where we are in time. And that gives the paleontologist actually a lot of control to either speed up drilling or slow down drilling. I actually have a very embarrassing story about that I can tell y'all later. But this is me in the paleo lab. It's a very long space with microscopes. So here's where I was 12 hours a day for 2 months. And if not there, you're writing and doing report work. Okay, so we got started, and the first stop was site U1506. So this is in the northern part of Lord Howe Rise in relatively shallow waters. So what you're looking at is kind of a CAT scan of the upper water column and through the sediments. So what people do when they take these images, they pull this device behind a ship, and that device shoots down energy through the water column into the seafloor. And when it hits a change in density, a layer that's a change in density, it sends a reflector back to the ship, and we can map that. So here's the seafloor, there's the water column, and notice this big feature down here. We didn't know what this was. Some people thought it was granite. A drowned reef was really common, and one of our scientists even thought it was like a fairy castle. When you're on the ship, you get really goofy. So we weren't actually sure what this was. It was pure discovery. And when we drilled it, this is what we found. It was actually basalt. And this is really cool. So what you're seeing in this core, this is youngest to oldest over here. This is sediment that was deposited in the water column, but this is basalt. This is volcanic rock. And what I want you all to notice is this volcanic rock, do you see how reddish it is, reddish brown in color? And it has holes in it. We think that was erupted when Zealandia was above the waves, before it sank below the seafloor. In other words, this part, when those volcanics erupted, this was above sea level or near it. So we see several flows. So here's that weathered top, then you get into more nice basalts. You see another top layer here with the brown, the weathering, and then you see some other layers in here. So we identified several of these lava flows, or basalt flows. We noticed that they had large gas bubbles in the tops of those flows. And we also noticed that one of these cores had what we called a Neptunian dike. It had a massive crack in the middle of it. It's this core right here. And this was refilled in with cement from calcium carbonate. So this is a type of rock that's common. It's a limestone. And when we started to look at it, one of the sedimentologists on the ship said, "I think there's fossils in here." And I was like, "Are you serious? No way." So I had the techs on the ship make a thin section, and we looked at those thin sections under the microscope. And this is what we found. There's things in here, bryozoan. There's mollusk fragments. This is green algae. We know this is a photosynthesizer. It had to be near sea level. This is an ostracod, a slice through the half of it. That's an ostracod, a slice through the entire thing. We found lots of cheloids and pellets, benthic foraminifera. We also found, well, it was just loaded with mollusk fragments. So all of these things together indicate to me that these basalts were erupted into a lagoonal environment or some type of environment that was close to sea level. Because a lot of these critters, again, these are photosynthesizers, it was packed with algae, mollusks, ostracod, especially the pellets, benthic foraminifera, those are all found in more shallow waters together as an assemblage. So this was also, these basalts also represented eruptions on Zealandia, again, when it was above sea level. So it was about this time when we started attaining a lot of attention on the news networks globally. When you drill a site, you have to put out a report, and that report is publicly accessible by everyone. So we wrote this report that we'd found drilled into these basalts, and people started interviewing our co-chief scientists, and they took that as us drilling into Zealandia, which we had. So we attained Paleo fame, HuffPost, Reader's Digest, all these places picked us up, but we had no idea. We were in the middle of the ocean. We don't have great internet. We didn't know what was going on, so we were like, cool, let's drill the next site. Okay, so two other sites that we drilled were U1508 and U1509. They were here in the Renga Basin, so right over here, again, close to Lord Howe Rise. And again, here's one of those images showing density differences down through the sediments. Notice that some of these are really folded. We wanted to know what caused that folding and what was the timing. When did those folds occur? We also wanted to drill into sediments that could help us reconstruct the climate of this area. And this is what we found in the sediments. So we found a lot of older fossils and younger sediments, a lot of reworking, which is prone to happen when you're working on like a coastal or slope environment. So notice there's this big slope here. We also found a lot of shallow water fossils. So things like crinoids, which can live in deep to shallow, bryozoans, bivalves, echinoderm spines, brachiopods. This is a tiny these were all taken with scanning electron microscope images, so they're very tiny. We found fish ear bones or otoliths, and one of our paleontologists that worked with us subjected those sediments to hydrofluoric acid, HF, which is a very strong acid. We could only do it when the wind was blowing the right way, so the fumes would be pushed away from the ship and no one got their lungs burned if they inhaled it. And so what HF does, it dissolves all of this more mineralized stuff and it leaves behind the organic matter. So we found insect remains. This is the lining of a benthic foraminiferal shell. These are pollen and fern grains. This is a dinocyst. We think it's a resting cyst of some type of critter. But what was of most interest to us here were these angiosperm pollens and these fern spores right here. So those came from sediments that were Oligocene in age, early Oligocene in age. And this is what the Earth looked like during the early Oligocene. This is a SCOTIS map. There was ice at the southern hemisphere, not as extensive as now, but this is the approximate location of where this site was, or where Zealandia was. It was located so much more south than it was today, so very high latitude. These angiosperms, the ferns, they indicate that the climate there was actually pretty warm. If you think about where a fern grows today, it's pretty swampy, or they can be kind of shaded, but they're in the woods. They're common here in New York. So that indicated that the climate there was warm enough for these angiosperm, these flowering plants, and these ferns to grow and proliferate. So pollen that we recovered indicated that was very warm regardless, during this time, regardless that Zealandia was located at such high latitudes in the southern hemisphere. After we drilled those sites, we then had to wow. Wowing is waiting on weather. We had a massive storm come up from the Southern Ocean. These are really common. They develop there in the Southern Ocean and they'll tear through the Tasman Sea. So we had to be very careful about storms during this time of the year. So when rough seas happen, what we do is strap down everything. There's TV monitors all over the ship, tell us to put away our glassware. The bookcases have straps on them. We make sure there's nothing that can fall over, and they tell you to secure your belongings. This is taken in the Paleo Lab. May works with ostracods, and Claudia is one of the world's nanofossil specialists. So we're all biostratigraphers, and we're just laughing because it says, wow, we thought it was hysterical. Again, when you're on the ship, everything's funny, or not. And then we went outside. So this is us. Notice our hair is going wild. The wind was magnificent. These are waves. If you walk out of the ship, usually the seas are down here, but I was standing back about 20 feet and the waves were coming up and sometimes over that bow. Is wild. And then we got a wild hair and decided, well, let's just go to the top of the ship and hang on to the pole. We had to hang on to this railing or else we would have been blown backwards. We had to put our mouths in front of our faces so that we could actually breathe because the wind was coming at us so fast, we couldn't even suck it in. It was unreal. We had a wonderful time, and then they closed the deck off because they realized that the scientists were going bananas and they didn't want us to get hurt. Fair enough. So the highest waves that we experienced during this time were 20 feet. And yeah, I did get a little seasick during that time. A lot of folks were far worse off. And we had to sail 300 nautical miles to the north. So we lost quite a few drilling days before we could come back to the south and finish drilling these sites. So during this time, when the waves chilled out a little bit, it was our captain's birthday. His name was Jack, so Captain Jack. He wasn't allowed to mix and mingle and party with us. It's like a professional thing, which I get. So we had a party anyway in his honor, and we had a pirate party. So we grabbed cord liner, it's just foam. We made, of course, swords out of it. We just went full goof and had a great time. So the Joides does have its own entertainment area. It's like a theater on the ship, and we just cleared all the chairs out. We put black lights up. These are the techs. They helped us put all the lights up, and we just blasted music and danced. And I can tell you that is amazing having a dance party on a ship that's also moving and doing this in the water. We were just being thrown everywhere. It was really cool. Okay, so then we were able to drill our last site. So this is in the abyssal plain. So we were drilling this site. We had to sail to the south. The water depth was a little over 3 miles. So remember when I was telling you about how we build that drill string? This took a few days to build because they had to build that drill string 3 miles until it hit the seafloor, and then we drilled further into those sediments. So at these depths, you don't have preservation of a lot of the fossil material. What you only pretty much get is dust that gets blown from the continents. So that dust contains contains iron, and when iron interacts with water, it rusts. So that's why these sediments were red. But what was really cool about these sediments too is that they had these white and kind of off-green layers in them, and we weren't sure what they were. So we did some research, and it turns out there used to be some volcanic activity in the area millions of years ago, and we think that hot waters that ran through the sediments from that volcanic activity actually bleached these sediments. Further evidence of volcanic activity was the presence of these certain minerals. Can y'all see this? These little dots here in the middle of that core? That's copper. Copper grew in these sediments because there was copper ions in that water that was running through these sediments, and it concentrated there and copper grew. We'd never seen anything like it. It was incredibly, incredibly cool. So we're heading back to port in Tasmania, the southernmost part of Australia. And you know you're getting close to port when the dolphins come out and start playing in the ship's waters. So that was us coming into port. This was taken by Brian Huber. He's a curator of the Cushman collection, the Thorium collection at the Smithsonian. This is our good friend, Kim McLeod. The first thing you want to do when you get off the ship is I just wanted a salad because we ran out of greens. And then you move on to other beverages. So here's us having a great time. This was the last selfie on the ship. So again, they sailed on an expedition after ours. So we had a little crossover party with them. And then everyone heads home. There's a lot of tears because you actually realize that these people become your family when you're with them nonstop for 2 months at a time. Okay, so let's move on to part 3, expeditions 390 and 393. This took place in the Southwest Atlantic Ocean. Again, these were two separate expeditions. They each sailed for 2 months at a time. However, all of the scientists that sailed worked together. It's kind of one big expedition together is how we think of it. We just had so much stuff to drill, they were implemented as two different expeditions. And here's where we drilled. So we're just moving from the Pacific Ocean right on over into the South Atlantic. So similar latitude, still in the mid-latitudes, but again, just the Atlantic Ocean. So what you're looking at the top of the screen, top left here, is a map of the age of the seafloor crust. So that red area, that really warm color, that's the youngest crust. And the bright red is 0. So that's the youngest, the new stuff. The cooler colors going out here are the older crust. So that stuff is way less dense. And what we wanted to do was drill 6 sites that cross or on the western side of the mid-Atlantic ridge. So these are those 6 sites. They're here. And do you remember early in the talk, I mentioned DSDP Leg 3? That was the expedition, the third expedition that sailed, and they drilled sediments that provided evidence for the theory of plate tectonics and seafloor spreading. Those sites are right here. So we were kind of almost re-drilling those sites and revisiting those famous holes that prove those theories, where those theories were developed. So for those of you that are not familiar with the mid-ocean ridge, this is just a schematic to kind of orient you. So this is the Earth's crust, and this is the asthenosphere. So we have this magma that's pushing up, and it's erupting in these ridges in the middle of the ocean. Again, that's all of this young stuff here. They're all over our oceans, and they've been there for a long time. So the very young stuff is here. That's age 0. So here's the mid-Atlantic ridge, age 0. And then this stuff, as it cools, that basalt cools down and flows on either side of that ridge, it becomes very cold and dense, so it sinks downward. So here's that older stuff. These sites were drilled from the younger part to the older part of the crust. So the coolest thing I think about seafloor basalts is that they have microbes that live in them. And this is kind of a new area of research. So those volcanic rocks that originate from mid-ocean ridges, people have studied them and actually found diverse communities, microbes and microbial communities in them. So this was a study by Suzuki and others that they just published in 2020, so still relatively new. And they looked at basalts that were 33.5 to 100 million years old. And these are their basalts here and here. And then they subjected those basalts to green dyes, green biologic dyes. And what they were looking for were microbes. So this green here and that green in there, those are all microbial communities. That's really cool. That's fascinating. What they did then was genetic sequencing of these microbes. So this is what they came up with. I'm not going to go through this whole pie chart. It's kind of late in the evening for that. Plus, I'm not a micro person. But what they found was this really, really diverse microbial community. So different types of species and genera of these microbes. And I'll also mention here that looking at microbe communities in seafloor basalt is a really new field. You can only get to these microbes by scientific ocean drilling and riserless drilling. It is one of the largest unexplored ecosystems on Earth right now. We have no idea what's down there. And some of my colleagues are also studying viruses that may live in these basalts. It's just mind-boggling and amazing. So what we also, the other part about the sites in this location that's really neat, because these basalts are very young and older, the sediments atop of them are also kind of younger to older as well. So this provides a really nice transect to study what ocean circulation was doing through time. So what you're looking at on the left side of the screen are some east to west profiles across those sites that we drilled. And you'll note that this gray area is just the seafloor topography, like the bathymetric profile. And there's these different names on here, these different abbreviations. So Antarctic intermediate water, that's one certain type of water mass. North Atlantic deep water, this is the deep water that originates in the North Atlantic. And there's Antarctic bottom water. These are bottom waters that originate around Antarctica. So notice that each of these water masses, this is temperature, this is salinity, and this is phosphate. And don't mind the colors, just note how they all change with respect to these different water masses. So NaDW here is green. What we wanted to do was look at the differences in these water masses through time and how they've changed. So now on the right side of the screen, what you're looking at are different paleogeographic maps of the Earth through time. The top is the Eocene Earth, what Earth looked like about 50 million years ago. The middle is a Oligocene, about 35 million years ago, and the bottom is a Miocene, about 20 million years ago. So note that the Earth is starting to look more and more similar to today, but the configurations of the continents are very different, and the surface and deep ocean currents were probably operating a little differently too. So it's not really well known or well constrained how these different water masses changed or did not through time when the continents were beginning to rearrange themselves, and also across ancient cooling and warming events. So some outstanding questions for this part of the world are there microbial communities in the South Atlantic, and what's there? This map of the Earth, these red and green dots, show the places in the world ocean where we have drilled and looked at microbial communities. Notice this big box with a question mark? We've never drilled for microbial communities in the South Atlantic, so we don't know what's there. We also don't know how ocean circulation, these different water masses, all of these things, how have they changed through time in this region? And how have they changed in response to, again, global climate change? So to answer the first question, what we did was drill into basalt, so that rock that underlies the sediments in the ocean, and look at those different microbial communities and sample them. And then we also, to answer that second outstanding question, was to recover sediments to reconstruct the ancient climate in the region. So the start of Expedition 393 was a little rough because this was after COVID last year. So the scientists did meet in Cape Town, South Africa. So there's Table Mountain, if you can see it in the background in the big port where the Joides was. And we had to quarantine the scientists had to quarantine for a week in a hotel to make sure no one had COVID. And then we were able to board the ship. A lot of scientists couldn't actually make it to the ship because of visa issues. One of the scientists, who was a graduate student, this would have been her first expedition, she tested positive for COVID on the last day of the hotel quarantine. Felt so bad for her. And one scientist was not able to get a flight out of New York because this is when Delta was having their issues. I'll let you guess which scientist that was that could not get a flight out of New York. So you have a pity party and you get over it, and I worked with the co-chief scientist to figure out how I could contribute to this expedition. So what I did was, because I was supposed to be the senior biostratigrapher on this expedition, the other biostratigraphers were graduate students, so I felt pretty awful about that. But I was in close contact. Thankfully, they were in a place where they had really good satellite connection and internet connectivity. So we worked through Slack, and Martine and I, the other paleontologist who worked with Thoriums, talked every day. He sent me data. I synthesized that data, and I helped write the reports for the ship. I also was able to help with science communication and outreach on social media and on Time Scavengers, my nonprofit organization that I co-founded with my friend Jen. And what we did was have the scientists write profiles about themselves on our Meet the Scientist blog so the public could get to know the scientists that were sailing. So every expedition has 2 outreach officers that sails with them, and Tessa was one of our outreach officers on that expedition. They recovered really great sediments. So here's some different holes that they cored. These 2 are phenomenal. They have different colored sediments. These are due to changes in ocean chemistry. When we go from this white to brown to darker chocolate brown color back to more lighter colors. The sediments that are very light colored are that color because they have a lot of microfossils in them. You'll notice this one is almost completely white to tan colored, just full of fossils. We also had really great recovery of basalts to study those microbial communities. So you'll note all the different colors of these basalts. This one has a lot of calcite infilling, so it looks like a lot of rubble of basalt, and then all these other minerals kind of mineralized in there, and they were very beautiful. So a lot of the scientists are conducting work on these now. So I'm thankful I was still able to be involved with the expedition heavily. And because I was a scientist that was chosen to sail, they've still given me access to all of the samples. And my graduate student, Ravi, who started with me last year, were able to go down to College Station, Texas, where one of the 3 core repositories around the globe. And what we did was scan these sediment cores. Now, the cores that he's working with are from the Middle Miocene. This is a time in Earth's history where we had a major warming event due to a large igneous province erupting. So Earth's atmospheric CO2 got to around 500 parts per million. So again, it's another analog climate state for what we may be experiencing in the future. And he's looking at atmospheric and surface ocean changes during these times. So this machine, you put the whole core in there and it scans it and tells you what elements are there and how they change through time. So we did that. This is one of our other outreach officers, Laura. She was able to come down and she's doing a Zoom call with the class, and Ravi's showing them the process of scanning. Here's the whole core room. It's behind the reefer where we keep the cores, which is basically a giant warehouse refrigerator. So it's pretty cold. We took a break to go sample some fossils just for fun. They're of Eocene age. And breakfast tacos. When you're in Texas, you have to get breakfast tacos. They're phenomenal. Okay, so just to wrap up really quick, we'll talk about Expedition 403, the Arctic Ocean. So this is an expedition that will take place here. It's really in the Eastern Fram Strait, so leading into the Arctic Ocean from the North Atlantic. So it's off the northeast coast of Greenland. So there's a lot of currents in this area of the world ocean. A lot of them are warm water currents. So this is a map of the North Atlantic into the Arctic. So here's that North Atlantic current, and here's that warm water current. They kind of come around Svalbard as well. This is kind of a close-up of that area. Here's Spitsbergen, and here's this West Spitsbergen current. So we want to look at how these currents change through time, again, across analogous warming and cool periods of today. And this area is also very under-drilled compared to other parts of the global ocean. So this figure is pretty chewy. Don't worry about that. It goes from 7 million years on the left to today. And note that these are just climate proxies for the last 7 million years. And all I want you to know is that they go up and down in response to the amount of CO2 and temperature on the Earth. So this is the area we're drilling across. These are the sites that we will drill and how much sediment, or the age of the sediment, we expect to recover from each site. So we're hoping that we're going to get sediments that go back to 7 million years. We're not sure. But one thing that I want to do on this expedition is see how this warm water current has changed across these warm and cold events of the last 7 million years. So these are the outstanding questions, which I basically just got ahead of myself instead. How did these currents respond to warming and cooling events of the past 7 million years? Because again, that can tell us something about how these currents will behave in the future. We also want to look at how the ice sheets in the eastern Greenland and in Svalbard have changed across those ancient warming and cooling events as well. Again, to give us insight into how these ice masses may change in the future. So we're going to recover sediments under the modern day position of these warm water currents, and we're also going to recover sediments that were close to Greenland and Svalbard to accomplish those missions. Okay, so we are leaving next June, early June, and we will come back in early August. These are the sites that we're going to drill. They're here. There's an expedition currently going on right now on the northwest part of Greenland. These are images from their expedition. There's an iceberg. They have to watch out for icebergs, and that's what they're doing in this video. This is at night. It's snowing. They have searchlights out, so they are looking for icebergs because if it'll be like a Titanic situation, but not as dire, they could harm the ship. And just beautiful views of sunsets and sunrises. Okay, so just to wrap up, scientific ocean drilling. We have a long history of success. It began with Project Mohole in the 50s. We have to date recovered thousands of kilometers of core since we've been drilling. For Expedition 371, the sediments that we recovered, our research actually has rewritten the tectonic history of the Tasman Sea. We've had a lot of paleoclimate papers come out from the sediments that we work with. And my lab is especially continuing to work with these sediments, and we're working on a big paper that's coming out too, hopefully soon. For Expedition 390 and 393, we've just received the sediments not too long ago, so my PhD student Ravi is beginning to work with them, and we'll be presenting at GSA this year. And the microbiologists have already begun to find and characterize microbes in those basalts. And for Expedition 403, stay tuned. Hopefully I'll be tweeting a lot, so if you are on Twitter, what is now X, follow along. I'll let you know what we find. Okay, I am happy to answer any questions, and I have stuff up front. I can bring them down. A drill bit. I've got pieces of Zealandia here, so you can see the differences in that worn and weathered basalt and differences in like the fresher basalt. I've got pieces of Antarctica and also pieces of the basalts that we drilled on 390. Thank you.
Bring the microphone. Take the microphone to the people.
Is that right? Any questions? All right. Here, let me take this.
I think I can project my voice. Well, it's for the recording.
Yeah, we're capturing this.
When you drill, do you have to mitigate for protecting marine mammals? And how do you do that? Are there sounds and any concerns? Have there been any history of harms to marine mammals through your drilling? Thank you.
Yeah, great question. When we're drilling sediments, no, it's actually pretty quiet because most of the action is taking place sub-sea floor. And we don't take up a lot of room. Like when we're drilling, that big, that's like the hole that we're drilling, right? It's tiny. The only time when we have to go on mammal watch, and scientists and some of the staff are some of the other scientists will take binoculars and just look out for any breaching whales or dolphins, is when we're shooting like sonar or doing other stuff like that. And we don't do that very often. That's only under particular conditions or when we need additional data. But we do. If we're doing something like that that's going to disrupt mammals, we absolutely have to be on mammal watch, and we have to abide by laws that state if they are near, we cannot do anything to harm them or that would disturb them. So yeah, great question. Thanks for that.
Thanks. That was a great talk. A lot of fun. I wanted to hear about the embarrassing story of your Time Lord and controlling.
Okay, thank you. When I sailed on 371, I was a wee grad student. I was in my second year of my PhD. And you have to understand, when I did my master's, I was working with invertebrates from the Ordovician, so 450 million years ago. So when I sailed, I was really like learning this stuff immediately and then applying it on the ship. And I was still very unsure of myself and questioned everything. So we were drilling this one site, and it was in the basin, and this was closest to the subduction zone. And we were drilling, and we were in the same age sediments for a really long time. And then all of a sudden, so everyone wanted these hyperthermal events. So these are in the Eocene when the Earth got really warm for a really short period of time. And they wanted to study those, and they wanted those sediments. The nanofossils were really badly preserved, so we could not use them for age control. So it relied on the foraminifera. So there was another foraminifera person there, Hugh, but his specialty was benthic foraminifera, which aren't as really great for age control as the planktic foraminifera, the ones that live in the very surface ocean. So the age control was on me, and I was like, this is it. This is my time to shine. I got it. So I found a species, its evolutionary event, that put us about 1 million years above one of these hyperthermal events that everybody wanted. We had not recovered them from previous sites because it turns out that when these hyperthermal events happen, the sediment type changes and that sediment is prone to falling out of the core. Even though we have a core catcher at the bottom, it's very soupy, so we were losing it. So I went to one of our co-chief scientists in charge and I said, Jerry, we're 1 million years above the MECO. We need to slow down drilling. So he's like, okay, I'll tell the drillers. So we slowed down drilling to half cores. And this took more time. Well, then it turned out, so it was taking a lot of time. People were very excited because the news has spread. Oh my gosh, we're gonna get the MECO. No. It turns out that we were in a reversal. So we were in a big pile of sediment that was older up here, slumped down, and just fell on top. So I was in an age reversal. So I had told the entire ship and the drillers to slow down drilling based on what I thought was something, an event that we were close to. And it turns out that we were very far from it. And Hugh, the other paleontologist that was with me, he's like, there's no Hinkanina spines. This is a foraminiferous species that has these very beautiful spines that everyone looks for. He's like, it's weird there's no spines. And so when I found out, when we got the nanos back, and it turned out that actually, no, we were not really close to this interval. And they were like, oh, we just lost so much time drilling. And I was like, oh my God, I'm so ashamed. And he's like, I should have known, there's no Hinkanina spines. Anyway, it was very embarrassing because, again, second year PhD student, and I had told this entire ship to slow down drilling. Anyway, it was a big learning moment, so it was embarrassing.
Any other questions?
How did you find your passion for all of this? I'm just curious because you seem very interested and very passionate about it.
By accident? I went to James Madison University because I liked where the location was in the mountains of Virginia. And it was far enough from home to be far from home, 2 hours, but also close enough that I could drive there on the weekend. So I was testing my ability to be away from my family. It ended up, that's where I met Kristen St. John, my undergraduate advisor. And I took a class with her called Paleoclimate. And it was a course-based undergraduate research experience. So Kristen had obtained sediment cores from the Gulf of Mexico, and it was her first iteration of teaching this course. And what she had was her 11 or 13 students do different tasks as if we were on the ship processing these cores. And part of my task was to look at the fossils in them. So I've always loved miniature things. And when she taught us about the ship, I was like, whoa, I want to do that. That's so cool. Like, I can't imagine. That's so far from like anything I'd ever dreamed that I could do or that people did. And I really fell in love with these tiny fossils. So then I went on and did a undergraduate thesis with her and presented at GSA. And we did some geochemical work on the thoriums, stable isotopes. And that's when I met Mark Lecky at UMass Amherst and went up there and worked with him and his students for a couple days. So it wasn't, like I said, by accident. It was just chance that I went to James Madison, found Kristen, and we're still good collaborators. We're actually going to present a poster with one of my other PhD students who also did her graduate degree at JMU and also worked with Kristen and also took her CURE class. So it's very full circle on these CURE courses and how they like help diversify geosciences and how they also help folks find a way into IODP and provide opportunities for them. So yeah, I don't know how good of an answer that was, but I just fell in love with it.
Thank you. Great stories. Any other questions from the audience? All right.
Thank you. Was the ship just diesel or was it bunker fuel also?
It's diesel. So it's run by train engines that were built in 1978. So we have, I think we can store like 1,000. No, there has to be more. I can't remember how many gallons of diesel we have on the ship, but it's enough to keep us at sea for actually more than 2 months, especially when we're transiting far distances. Like in the Tasman Sea, for example, we had to sail from Townsville, Australia, all the way out into the middle of the Tasman. So that took us a few days. But yeah, these train engines are another reason why the Joides is kind of getting older and it cannot sail after 2028. It'll be too old, and there's some maritime rule that I don't get. But we also have like a machinist that sails with us, because if any of those train engine parts breaks, you can't get them anymore. They're not made anymore. So they actually have to machine them and make them.
Now, does Schlumberger or Halliburton share core samples with you when they drill a dry hole?
So we don't share samples with them because it's all taxpayer funded. We have an agreement that we keep all of that material. And it's open access to educators and to scientists. So like we can request any of that material that we've drilled, and you can say it's for research or you can designate it for teaching. So educators can request this stuff for their classrooms too. What we do use is Schlumberger's tools because they're downhole logging tools, so like resistivity and stuff like that. We do contract out with them to do that sort of stuff because IODP doesn't have their own tools. They're so expensive. So we do have a rep from Schlumberger that does sail with us.
Hi, that was a really good talk. During your master's and PhD, at any point, did you feel that you wouldn't be able to accomplish something, or were you fully confident in your convictions?
Oh, no. Nope. There were times during my master's where I would call my husband crying and be like, I want to quit. I hate it. I didn't have a good time in Ohio. I found this house and it said grad students only. And anyway, long story short, I ended up rooming in a house with 13 other people, and some were undergraduates and some were like mechanics, and one dude was trying to be a rapper out of his mom's basement. It was a very weird situation, and lots of strange things went down in that house. So anyway, it was stressful home life. My husband was always a big support system as well as my family, and I just call them and be like, that's it, I'm done. And they're like, Adriane, get it together. You're going to be fine, just push through. And they were right. During my PhD, I had a better time. I really loved my advisor. Not that I didn't love my master's advisor, but my husband and I were on our own for the first time in our own apartment, so it was a very different situation we were in. And we also had his income, which had increased, so we were a little bit more financially stable too, which also made a huge difference. But yeah, there were plenty of times when I kind of thought, what am I doing? I can't do this. And there, especially when the research gets tough and you're on tight timelines and then the writing is awful, you just push through. Yeah, that's a great question. Thanks for asking that.
Any more questions? All right. Well, thank you very much for all of the sea stories and wonderful science.
Thank
I
y'all.
think if I can
Appreciate
get this
it.
back in here, then I can. There we go. All right. One more round.